This screencast is going to go over the homework that we had, multiple choice questions from, this was 2016's multiple choice from the AP exam, only on Big Idea 5 and 6. So we're looking at equilibrium, acid-base, and thermo. So number 9, here we have a nice acid-base titration, and plots the experimental results in this graph, which best explains the experimental findings. The correct answer for this one is C. A weak acid is titrated with a strong base, as evidenced by the equivalence point of a pH greater than 7. All right, so our equivalence point, remember, when it starts to do this straight up and down thing, it's halfway through here. So our equivalence point for this one is right around a pH of 9. Plus, the shape of this part of the graph lets us know that we have a weak acid. You have that sharp intake, and then it kind of levels off as that buffer system builds. Okay. Next, number 4, we're looking at the Haber process here. And for this question, the correct answer is D. So we're making some ammonia in the presence. We have an a less than 0. Delta H is less than 0. So that means this is exothermic. So that means heat must be given off. So it is a product. And which of the following changes will result in more ammonia in the mixture? Well, for D, you're going to add NO2. It's going to shift to favor and make more products. All right. All right, then if we look at number 20, the correct answer here is A. It's asking for which of the following is the strongest acid. They give us a piece of information that K is greater than 1. K is going to be our products over our reactants. Again, raised to that coefficient power, but we don't have to do that here. And if it's greater than 1, that means we have more products than reactants. So this reaction, where it's going to fall with equilibrium, we're going to have more of this than of the reactants. So for a strong acid, remember strong acids don't have as, well, they don't undergo equilibrium. So if we're talking about a strong acid like hydrochloric acid splitting up, it's a one-way street. It splits up and does not go in the reverse reaction. So if we're talking about which one's a stronger acid, it's going to be the one that stays split up more. And since this reaction favors more products, that means this hydrogen wants to come off of what it's bonded to more than this hydrogen right here wants to come off of Y, which makes HX the strongest acid of the ones that are provided. All right. Then if we look at number 12, the correct answer for number 12 is A. Based on the KSP values, which of the following compounds has the highest chloride ion concentration? So we're talking about which one is going to split up the most. So if we look at all these KSP values, the smaller the KSP value, the less soluble something is, the less it wants to split up. So we need to look for something that has the highest KSP value, and that's going to be our lead chloride. This is quite a bit higher. This value right here is quite a bit higher than all the other values, and especially in considering that it has to have that chloride ion squared. So it is going to have our highest concentration of chloride ions because it has the highest KSP. All right. Then we get to this one right here, another acid-base titration curve. And the correct answer for this one is going to be A. It's asking about point R. Point R is the equivalence point. So that's when the moles of acid are equal to the moles of base. And at that point, we only have a salt. So again, if we're dealing with HCl and NaOH, we're going to get NaCl and water. And if we have 10 millimoles of this, and we have 10 millimoles of this, that means, and we have none of this at the beginning, at the equivalence point these would be equal, so we're going to be losing those but creating more of the salt. So what we would have at the equivalence point is just the salt in solution. Number 23, we're talking about that same titration. And in this case, we're going to change the concentration of HCl from 1 to 1 from 0.1. How would the student's titration curve differ from the original one? So the correct answer for number 23 is D. The pH far beyond the equivalence point would be lower on the curve. So this part of the graph would go lower because I've got more acid, which is going to make the pH quite a bit lower. Maybe not all the way to 0, but pretty low. All right. Number 40. And number 40, the correct answer is A. So with this one, we're dealing with bond energies. So it is going to be breaking minus making. So I'm going to have to break the HH bond from H2, and I'm going to have to break this Cl-Cl bond as well. Then the new bonds are going to be formed, so I'm going to make the HCl bond. But you have to notice the coefficient here. So there are actually going to be 2 of these HCl bonds. We have the bond energy of this one as being 430. This one is 240. So if I add those together, that's going to give me the energy it takes to break the old bonds. The new bonds being formed, that's 430 and 430, so that's going to be 860. So the bond, more energy is released than taken in, because energy is required to break old bonds. So in this case, the reactants on our energy diagram are going to be higher than my products. So here it took in some energy, but about 670 kilojoules of energy, and then more energy was released when it made these HCl bonds. And that was about a difference of almost 200. All right. Then if we look at number 24, the correct answer for number 24 is B. So in this case, we are reacting hydrochloric acid and sodium hydroxide to determine the amount of heat released. We vary the amounts or the volume, but the concentrations stay the same. In this case, in trial number 1, they're going to both run out at approximately the same time, and we would end up having none. In the second trial, we're going to have excess HCl because we just have more of it. And so this is going to be my limiting reactant, which happens to be the exact same as in trial 1. So the amount of heat released for X and Y are going to be equal because the same amount are going to be reacting. Here, 50 milliliters of NaOH is going to react, and in the second one, it's going to be 50 milliliters because when I run out of NaOH, the reaction is going to stop and no more heat will be produced. All right, then if we get to number 25, the correct answer for number 25 is A. So for this one, you just had to do a little bit of math. I start to see I've got amounts of this and of NaOH and HCl. Then I have a temperature change, and then they give me the specific heat, and they give me a little blip about the density of water. All right, so that already makes me think that we're looking at Q equals MC delta T. And that's how we're going to be able to find the kilojoules part of our answer. So for the mass, well, we don't have a solid here. We have two liquid solutions, but we're using 10 milliliters of each. And these are pretty dilute solutions. So they're mostly water, which allows us to use the density of water. So if I have a total of 20 milliliters of solution of liquid, that's going to be equal to 20 grams for my Q equals MC delta T. So it is the mass of the two liquid solutions. So 20 grams times specific heat 4.2 joules per gram degrees C, and then my delta T is going to be 6 degrees C. So that's going to be, doing some mental math, that'll be 84 times 6, getting rid of those, and so that's going to end up being 504. Now this is in joules because that is what my specific heat is given in joules. So we'll go ahead and convert that to kilojoules, since again our answer is in kilojoules. That's going to be 0.5, and we'll just go with that, kilojoules of heat. Now we have to deal with this per mole. Usually when we look at a situation like this where we have an acid and a base reacting, what the per mole part is per mole of water produced. So if I look at this and I have HCl and NaOH, it's going to react to form salt and water. So we're going to try and figure out the moles of this that are formed. So 1 times 10 milliliters gives me my 10 millimoles. And for NaOH, I've got 10 millimoles. When these two things react, we're going to use up these 10 millimoles. And we're going to add 10 millimoles of each of these. Now again, we deal with just water. That's just what they decided to do with acid-base reactions. It's per mole of water. So 10 millimoles. Now we got King Henry's Daughter Bakes Delicious Chocolate Muffins, so we're at milli. So we need to move this back 1, 2, and 3. So that is 0.01 moles of water. And if I take my 0.5 kilojoules and divide it by 0.01, that's the same thing as dividing by 1/100th. So I need to multiply 0.5 by 100. And just to write that out, 0.5 is going to be 1 over 100, and that's just 0.01. So that's going to be 0.5 times 100, which is going to be 50. And it's 50 kilojoules per mole. That heat is given off because our temperature did go up, and that's why it is negative. That was a fun one. All right. In number 44, the correct answer is C. So we have this reaction for breaking down methanol, and we see that it is an endothermic reaction as shown by this positive delta H value. What happens to the temperature of the contents of the vessel as the reaction occurs? It is endothermic, so the temperature must decrease, is really the only logical choice on that one. All right, then in number 46, the correct answer is C. What can be inferred about a delta S for the reaction? Reaction represented above essentially goes to completion. That lets me know that it is spontaneous. which means delta G has to be negative. Delta G is equal to delta H minus T delta S. If delta G has to be negative, and we know from up here that delta H is positive, that means this value right here must be huge, and delta S must be positive to make delta G negative. Okay, if we look at number 47, which is still related to the same thing, the correct answer for 47 is A. Here we're talking about the bonds. So when you see something about bond or bond enthalpies or bond energies, we're talking breaking minus making. For delta H to be positive, that means more energy had to go into breaking the bonds. So those bonds that were broken had to be much larger than the energy that was given off when we made new bonds. And so the sum of the bond enthalpies of the bonds in the reactant is greater than the bond enthalpies of the products. Okay, so then we get to number 33. And we're dealing with two slightly soluble salts. We see silver and lead, which often make things insoluble. We do notice that lead has a smaller KSP than silver. So that means that it is less soluble than silver sulfate. So we've got a solution, and it's got some silver ions, and we've got some lead ions in there, and we know the concentrations of those ions. And it is in a 1 liter solution, so our molarity is the same thing as our moles for those particular ions. And then we're going to add a source of these sulfate ions from the potassium sulfate. And we're going to add this many moles of it. The key to this problem is knowing that the one that is the least soluble will precipitate first. So what's going to happen, since this guy has a lower KSP, that these sulfates are going to bond with the lead and create the lead sulfate precipitate. And then because of these amounts right here, we actually are able to calculate or see that all the sulfate ions are going to be used up because they're the same. So we're going to take out all of our lead, and we're going to take out all of our sulfate. So that means the silver is going to stay in solution. It would only precipitate if I added way more of that potassium sulfate or had another source of those sulfate ions. So the correct answer for this one is C. It was a tricky little problem. All right. If we look at 34, the correct answer for 34 is B. So for this one, we've got a 0.01 molar solution of HNO2, and they give us the Ka is 4 times 10 to the negative 4. So this is going to be 0.0004 is going to equal my ions, so those hydrogen ions times my nitrite ions over the concentration of my HNO2. Now, from a result of an icebox on showing how that HNO2 splits up, you know that we're going to end up with 0.004 equals x times x, or x squared, divided by the concentration of our acid minus x, but in this case, x is going to be really tiny. So in this case, I'm going to be multiplying this 0.004 by 0.01, and that is going to give me 0.0. Okay, is x squared, so that's 4 times 10 to the 1, 2, 3, 4, 5, 6. So 4 times 10 to the negative 6 is x squared. So we have to take the square root of both of these. And so x is going to be something like 2 times 10 to the negative 3. And our pH is the power of the hydrogen ions. So this is equal to our hydrogen ions because it was x. And so our pH is going to be around 3, but a little bit lower. So it's somewhere between 2 or 3. And that's how you prove it with math. Otherwise, you probably would narrow it down to at least B or C, because it is a weak acid and not one of those that we know is a strong acid. All right, then we have number 32. In this case, you have to pay attention to this K. This is a huge K. That means we're going to have a whole lot of our products over here. Way more products than reactants. And if you think about an icebox, and I'll just write it up here, we're going to have a certain amount of this. We got 2 moles, so it's going to be, for our molarity, is going to be 0.02 and 0.02 initially, and you're going to have none of this. And then we're going to actually make some products, and we're actually going to make a whole lot of products, which means I'm not going to have very many of these reactants left. And we really want to make X small when we do things. So in this case, I would put X here. Whenever you're working with an ice box, it's always final minus initial. Even if you can't really wrap your head around it, that's going to be your change. And then it's moved over. But we already know that X is going to be really, really big. So these guys are going to be huge. So this is going to be 0.02 minus X. So we're going to have a lot of products. That means it can't be D. Water and CO are on the same side and they have the same coefficient, so it can't be A. We're going to get a lot of products. So the concentration of hydrogen would actually be much greater than the concentration of water. So that leaves us with C being the correct answer. We're going to have way more carbon dioxide, because that's one of our products, than we have carbon monoxide. All right. Here for 37, I thought this was a pretty tricky problem. You should have been able to narrow it down to C or D. The correct answer is C. The reason why you would have narrowed it down to C or D is that we've got some sodium peroxide, and it's 7.8, and we're reacting it with 3.2 grams of sulfur. In the second one, we double the amount of sulfur. Both trials yield the same amount of SO2. That means this guy is our limiting reactant, because it's the one that determined how much of the product was made. Now we have to deal with the Q. Remember, Q is related to delta H. This one is negative 610 kilojoules per mole. So that's kilojoules per mole of our limiting reactant in this particular one. And how many moles of our limiting reactant do we have? We have 2 of them. So for every 2 moles of sodium peroxide, we are going to be releasing negative 610 kilojoules of heat. So in this case, if we look at it, all right, so for this one, we're going to need to divide this. Oh, we've got how many moles of this? How many moles of sodium peroxide? So 7.8 grams, and we have a molar mass of 78, so that's 0.01. And so we need to divide by this, so that's going to give me, right, like 305 for the number of moles that I have. But again, this is per 2 moles, so I have to, oh, I'm sorry, that was per 2 moles, so negative 305. And then I have to divide it by the 0.01, sorry, 0.1. So that's going to give me the 3, sorry. Let me start over. So we got 7.8 divided by 78, and that gives me 0.1. That is where I knew some math was off here. Okay, so we have 0.1 moles of that sodium peroxide. This is per 2 moles of sodium peroxide that are leaving, so we need to divide this by 2. So that gives me that negative 305. And then I only have 0.1 moles, so that's going to make that decimal move over, allowing us to get that 30 kilojoules of heat. All right. Then we have number 39. The correct answer for number 39 is C. Which of the following statements is about thermodynamic favorability of a reaction is correct? In this particular one, our delta H is negative, so that's exothermic. Nature loves that. Our delta S, though, is also negative. That means it's going towards more order, and nature likes disorder. So the factor that is making this reaction spontaneous is delta H and delta H only. Delta S is because it's going toward more order. More order does not make something more thermodynamically favorable. And that's why the correct answer is C. And we know that this reaction occurs, so it is thermodynamically favorable. So the correct answer is not A. All right. 42. The correct answer for number 42 is A. And we have, okay. So for this particular one, we're putting 0.1 mole sample for each of the 4 species in this reaction. And what you have to do for this one is you've got to find Q, and then you have to compare it to K to see which way the reaction is going to shift. So anytime you're given K and then you're given some values of something that we're putting in, but they don't say it's at equilibrium, you've got to find Q to see which way the reaction is going to shift. So Q is going to end up being that CS2 times H2, and that's going to be to the 4th power over concentration of H2S squared and CH4. Okay, so I put 0.1 mole sample. It's in a 1 liter, so 0.1 is also my molarity. And so if I put this in here, and I'm going to put this in here a little strange. So to find what Q is, I know that CS2 is 0.1 molar. And H2 is 0.1 to the 4th power. So I'm just going to do 4 0.1s here, 4 additional ones to represent that H2 part. Then H2S is squared, so that's 0.1 times 0.1. And then CH4 is 0.1 molar as well. So now I can just get rid of some of these. So 0.1 times 0.1 is going to be 0.01. Yes. All right. And that's what Q is. K is 0.00034. That means Q on a number line is way over here. It's much larger than K. Everything wants to get back to equilibrium. So the reverse reaction, we would shift to the reverse reaction. So that means we're going to have more of one of those two. The reason why it's H2S is because we're going to get 2 H2S's for every 1 methane that is produced. All right. For for 43, the correct answer is B. So for this one, we're looking at a heating and cooling curve, and they're talking about the situation happening at X. We know that at this point, the liquid is boiling and being converted into a vapor. So this part right here tells us that delta S, vapor, is way more disordered than a liquid. So delta S is definitely positive. So we have it narrowed down to those two. And then if you just think about boiling, remember that it requires heat in order to get something to boil, and endothermic reactions require heat to get them to go. And so endothermic reaction means delta H is positive, giving us that B as the correct answer.